All right, we're going to start off today by looking at number 17 from the homework on page 483. Oops. All right, for 17, we have tan theta is equal to -3, and we're told that sine theta is less than 0. And we are asked to find sine of 2 theta, cosine 2 theta, sine theta over 2, and cosine theta over 2. So what we need to do here is we want to go ahead and set up our unit or our circle. Right, and if tan theta is equal to -3, so tan is negative and sine is also negative, that means we have to be in the what quadrant? First, second, third. Which quadrant is sine negative and tangent is also negative? Fourth. So yeah, we got to be somewhere in the fourth quadrant. All right, so there's our angle theta. And so, oops. Okay, and so if tangent is -3, then tangent is opposite over adjacent, right? And so we can treat -3 as -3 over 1. So we could say that the y coordinate might be -3. I should have done that in blue. And the x coordinate might be 1 of that particular point that crosses that that circle. And of course you want to figure out what the radiuses there are. So we have to do r squared is equal to 1 squared plus -3 squared. Set up our Pythagorean theorem equation for the right triangle, the reference triangle for that particular angle. And so if we go ahead and solve this, we get that r squared is equal to 10. So r is equal to the square root of 10. So we have all the things we need to find: sine, cosine, tangent. So we know that sine 2 theta, the double angle for sine, is equal to 2 sine theta cosine theta. Right, so we can figure this out just by plugging in sine theta and cosine theta. Sine theta is is y over r, which is going to be -3 over square root of 10, and cosine theta is is x over r, which is 1 over square root of 10, and so sine 2 theta ends up being -6 over 10, which reduces to -3/5. Cosine 2 theta, we know we have like 3 different formulas for that. I'm just going to use the first one: cosine squared theta minus sine squared theta. And so cosine, we already said, was 1 over square root of 10. Sine is -3 over square root of 10. And so we end up with 1/10 minus 9/10 for -8/10. Right, so -8/10 is what we end up with there for cosine 2 theta. For the half angle ones, sine of theta over 2 is equal to plus or minus the square root of cosine, or 1 minus cosine theta over 2, right? That was the formula, one of the formulas we derived, or the half angle formula for sine that we derived yesterday. All right, and so we know, and we, first of all, sine has to be negative or positive? Negative. So we can just drop the plus minus and just have it be negative. Square root of 1 minus cosine theta. Cosine is 1 over square root of 10, we decided, over 2. And so we get, if we combine this into one fraction on top, we get square root of 10 minus 1 over square root of 10. Whole thing is over 2. And so we get square root of square root of 10 minus 1 over 2 square root of 10. And we're just going to leave that as it is right there. We oftentimes are going to get square roots and sides of square roots with our half angle formulas just because of how they are. And then finally cosine of theta over 2 is going to be plus or minus the square root of 1 plus cosine theta over 2. Cosine has to be positive in this quadrant, so we just want the positive one. So we'll get 1 plus cosine theta, which is cosine theta is 1 over square root of 10. So we'll end up getting, if we simplify this all out, square root of 10 plus 1 over 2 square root of 10, just like we did the other one there. Okay, any questions about that? So we're just using our formulas there once we figure out sides of the triangle. Other questions about the homework? Yep. So number 24. We have, we're using the half angle formula to find the exact value of the secant of 15 pi over 8. So secant of 15 pi over 8 is the same as 1 over cosine of 15 pi over 8. So is 15 pi over 8 half of an angle that we do know? Because they asked us to use the half angle formula. So we can write this as cosine of 15 pi over 4 divided by 2, right? 15 pi over 4, is that going to have a special angle for our reference angle? Over 4. Pi over 4. What's the reference angle going to be? 45. So yes, it is going to be a special angle, so we can use the half angle formula for that. So it's going to be square root. And 15 pi over 8, cosine of 15 pi over 8, what quadrant is that in? Or sorry, 15 pi over 4, what quadrant is that in? Oh no, I take it back, sorry, 15 pi over 8, 15 pi over 8. Well, what quadrant is 15 pi over 8 in? $15 pi over 8 is in the second quadrant, right? Because it's more than pi. Well, is it going to be in the second quadrant? Because it's more than pi because it's bigger than 1, right? But it's less than 2 pi, isn't it? And is it, how is it in comparison to 3/2? Yes, it's almost 2 pi, right? Yes, it's in the fourth quadrant. So last guess was the best one, right? So 15 pi over 8 is in the fourth quadrant, meaning that cosine in the fourth quadrant is what? Positive. Right, so we want the positive version of this. And so it'll be 1 plus cosine of 15 pi over 4 over 2. So cosine of 15 pi over 4, if we're having trouble visualizing this, let's go ahead and draw a diagram. 15 pi over 4 is almost 4 pi, so it's going to be 1, and then all the way around here, right? 15 pi over 4 is just pi over 4 less than 4 pi, right? So 2 full times around. So that means it's going to have a reference angle of pi over 4, right? And it's going to be in the 4th quadrant. And so is cosine negative or positive there? So what should the value be? It is a pi over 4 reference angle. What should the value be? That's the value, that's the measure of the angle. That's not the value of cosine for 45 degrees, no. And positive square root of 2 over 2, because we're in the 4th quadrant, over 2. So we get 1 over, I'm just going to try and clean this up a little bit. 1 plus square root of 2 over 2 is going to be 2 plus square root of 2 over 2 divided by 2 is over 4, right? And so we'll end up with the 2 is going to end up, so we take square root of 2 of the bottom here, and that's going to, we can break that apart. Square root of 2 of 4 is going to be 2, and the 2 will come to the top because we're dividing by a fraction. So it'll be 2 over 2 plus square root of 2. And we could rationalize the denominator, but I'm not going to worry about that. So that's what we should end up with for that one right there. So you got to express it as the half of an angle and use the half angle formula there to be able to determine the exact value. Okay. Other questions from the homework? No? Okay. So today we're going to start talking about solving trigonometric equations. All right. So solving trig equations. I mean, they are what they sound like they are. They're equations that involve trigonometric functions, and the solutions of trig equations are just like the solutions of regular equations. They make the left side equal to the right side. So for instance, if I have the equation cosine theta is equal to 1/2, right? So what are the possible solutions to this equation that's going to make this a true statement? Values of theta that's going to make the left side equal to the right side, essentially make both sides equal 1/2. Right? Well, look, we're just asking ourselves the question, where is cosine theta equal to 1/2? Right? What values do we get 1/2 for cosine? So what angle? What's in 1/2 is a number that we know is associated with one of our special angles, right? So which special angle, if we take the cosine of it, gives us 1/2? Do we remember? Cosine is the x coordinate on the unit circle. Oops. 60. Yes, I would agree with that. So 60, that's one of them, but is that the only one? So 60, which is also pi over 3, right? And then also, well, let's just look at the ones that are between 0 and 2 pi first, that are all positive, and then we'll worry about the negative ones afterwards. What would that be in positive terms? It's 2 pi minus pi over 3, right? Which is going to be... Yes, 5 pi over 3. That doesn't look like a 5 very much. Let's try that again. So we have 5 pi over 3. All right, so the two angles that are going to give us a cosine of 1/2 are pi over 3 and 5 pi over 3. So those are the only two that are between 0 and 2 pi. So we haven't specified an interval for theta. So if I don't tell you that theta has to be between like 0 and 2 pi, then you have to give me all of the solutions. And because cosine is a periodic function and it repeats over and over again, how many solutions are there going to be of this equation? Yeah, there's going to be infinitely many solutions if we don't specify a domain over which we're restricting theta to. So to be able to express those infinitely many solutions, we know that possible values of theta could be pi over 3. And what else relating to pi over 3? Any angle that is what to pi over 3 would also have the same value for cosine. Any angle that is what to pi over 3?
2 pi around the circle?
Yeah, if we go another 2 pi. So we call those angles, starts with a C, O, coterminal, yes. So any angle coterminal with pi over 3 is also going to have that. So to represent all of the coterminal angles at pi over 3, we're just going to write 2 pi k, where k is just any integer value. So if I add 2 pi, that works. If I add 4 pi, 6 pi, 8 pi, if I add or subtract any multiple of 2 pi from pi over 3, I will also get an angle that is coterminal with pi over 3 that's going to have the same value. So that's one possibility. The other possibility is 5 pi over 3, but also all the angles that are coterminal with 5 pi over 3 will also have the same value. So we'll do the same thing there as well. Add 2 pi k, right? So pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. If k, and we should specify, is any integer value, right? So if I plug in any integer value for k, I'll get a solution to that equation. So if I don't specify a domain over which theta is being restricted to, then I'm assuming theta can be anything, and for pretty much all of these trig equations, there will be infinitely many solutions, and you have to express your solutions to reflect that fact, right? All right. I'm going to give you another one to look at. So go ahead and solve the following equation by getting it to that same point and applying the same logic. And I'm not specifying any domain over which it's valid. So go ahead and solve that equation for me right there. And my recommendation is get sine theta by itself first. Isolate sine theta and then use the same process we just used right there. Also make that plus square root of 3. Instead of minus square root of 3, we're going to have that be plus square root of 3. So the first thing we want to do here is to solve for sine theta. So we'll get 2 sine theta is equal to negative square root of 3. So sine theta equals negative square root of 3 over 2. So sine is negative and it's square root of 3 over 2. So if it's negative, we know the two solutions have to be in the which quadrants? Third and fourth quadrants. So we know there's an angle in the third quadrant as well as an angle in the fourth quadrant that are going to have that value for sine, right? And so what's the reference angle that gives us square root of 3 over 2 for a value for sine? Do we remember? Pi over 6, yes. So it's going to have to be the angle that is a reference angle of pi over 6 in the third quadrant and a reference angle of pi over 6 in the fourth quadrant. In the third quadrant, that's going to be what? It's going to be pi plus pi over 6. So how many pi over 6s is that going to be?
7 pi over 6.
Yep. And in the fourth quadrant, it's going to be 2 pi minus pi over 6.
11 pi over 6.
Yep. So possible solutions are theta equals 7 pi over 6. So then I have to add 2 pi k for all of the angles coterminal with 7 pi over 6. Or the other possibility is 11 pi over 6 plus 2 pi k if k is an integer. Right? So that gives us all the possible values for theta there. Now, on the other hand, if I had said that, in this case, I don't specify what theta is, but what if I had specified that theta has to be between 2 pi and 0? If, on the other hand, I would said that, then theta would be equal to what in this alternate scenario here? What would I say? If I only want angles between 0 and 2 pi, I would say what? Yeah, that's pretty much all I would do. Now, it might get a little bit trickier if I made it like a weird domain. What if I said like negative pi over 2 to pi over 2? Then you're going to have to, so what if I said, yeah, let's do that right now. If theta is between, let's say, instead of between 0 and 2 pi, what if I said between negative 3 pi over 2 and pi over 2, I use some weird domain like that. Then what values of theta are you going to have? Then you could just start, taking values of k and figuring out which ones are going to be between 0 and pi over 2. So 7 pi over 6 and 11 pi over 6, neither of those are between negative 3 pi over 2 or pi over 2 if we just have 0 for k, right? So what about coterminal angles that might be between those two? Instead of 7 pi over 6, what if I subtract 2 pi from 7 pi over 6? What do I get? Right, so I make k negative 1 instead of, normally I just make k, to get these I'm making k 0, right? But if k is 0, then we get 7 pi over 6 and 11 pi over 6, so k 0 is not going to work. What if k is negative 1 here, if we subtract 2 pi from 7 pi over 6? How many pi over 6s will we have? So if I go and I make this, yeah, because I'm subtracting 12 pi over 6, so negative 5 pi over 6. Is that between negative 3 pi over 2 and pi over 2? Is it? Is it bigger than negative 3 pi over 2? Bigger in the sense that it's farther to the right in the number line? Between negative 3 pi over 2 and pi over 2? It is, yeah. So negative 5 pi over 6 is in that domain. Now what if I do the same thing with 11 pi over 6? I do 11 pi over 6, and I subtract 2 pi from that. How many pi over 6s will I have? Yep, negative just pi over 6, right? Is that between 0 and negative 3 pi over 2 and pi over 2? Yep. So those two work, right? And of course, if I go ahead and I subtract more than that, I'm going to get outside my range here. If I go ahead and if I subtract another 2 pi from these two, I'm going to be below negative 3 pi over 2, right? So we can stop there. And if I were to add 2 pi to either of these, they're just going to get larger. They're already too big because they're bigger than pi over 2. So clearly making k 1, 2, 3, or 4, any value bigger, any positive value is going to make these too big since they're already too big, even if k is 0. We try negative 1, and in both cases, negative 1 puts these both in that range, right? And if I were to subtract another 2 pi, then that's going to bring me below negative 3 pi over 2, and I'm going to drop out of that range again. So the only two possible solutions would be negative 5 pi over 6 and negative pi over 6, right? So, right, depending on how the domain is specified, the answers are going to be different. So the general solution, no matter if pi is not restricted, is always a good starting point, right? Figure out what the general solution is, and then try values of k, right? K being an integer value, that are going to put these in the domain that you're looking at, depending on what that domain happens to be, right? So let's go ahead and look at another. All right, so realize we made a mistake here. We got to fix this. It should actually be pi over, it's not pi over 6. It should be pi over 3. So 7 pi over 3. Nope, it's not even going to be that. Sorry. So instead of the answers being 7 pi over 3 and 11 pi, or 7 pi over 6 and 11 pi over 6, right, it should actually be, it's 60 degrees, which actually pi over 3 is the angle that if we take sine of it gives us a sine of square root of 3 over 2. So for negative square root of 3 over 2, we have to have a reference angle of pi over 3 in the third quadrant and the fourth quadrant. So a reference angle of pi over 3 in the third quadrant is going to be 4 pi over 3. And a reference angle of pi over 3 in the fifth quadrant is going to be 5 pi over 3. All right, so it should have been 4 pi over 3 and 5 pi over 3. That was, made a mistake there earlier. So 4 pi over 3 and 5 pi over 3. So for the general solutions, if I don't restrict the domain, then we'd be done at that point. Just 4 pi over 3 and 5 pi over 3. Right? And if I, once again, restrict it to 0 to 2 pi, right, then that would just mean that we'd use k is equal to 1 for our k value. And we would get 4 pi over 3 and 5 pi over 3 for solutions between 0 and 2 pi. And if we restrict the domain to negative 3 pi over 2 to pi over 2, then 4 pi over 3 and 5 pi over 3, of course, are both too big. So they're both larger than pi over 2. And so what we'll do is we'll go ahead and subtract. We'll make our k value equal negative 1 and subtract 2 pi from both of these to see if they end up in the right domain. So if I do that, I will get, so if I do 4 pi over 3 minus 2 pi, I will get negative 2 pi over 3. That is definitely between negative 3 pi over 2 and pi over 2. And if I do 5 pi over 3 minus 2 pi, I will just get negative pi over 3. And those are both between negative 3 pi over 2 and pi over 2. I could go ahead and subtract another 2 pi. I could make k negative 2, but then that's definitely going to put that outside of the range. It's going to make it smaller than negative 3 pi over 2 in this case, the case of negative 2 pi over 3. And if I subtract another 2 pi from negative pi over 3, it's also going to make it smaller than negative 3 pi over 2. So these are the only two that fit in this domain right here. So my solution would actually be negative 2 pi over 3 and negative pi over 3, if that's how I would have restricted the domain. So we have to be really conscious of the domain and make sure that we don't make a mistake solving the initial trig equation for the reference angles that, or the angles that have the reference angles that we're looking for. So just be careful that you don't make the mistake that I made. In a more complex manner here. What if I have, situation like the following, where I have sine of 2 pi now is equal to 1/2. Sine of 2 pi is equal to 1/2, and I'm specifying that theta has to be between 0 and 2 pi, not including 2 pi. So I've restricted the domain. Instead of just having sine theta equals 1/2, I have sine 2 theta equals 1/2, right? So we're going to use the same reasoning for figuring out what theta was before to figure out what 2 theta has to be. What values of what angles give me a sine of 1/2? Let me ask that question first of all. First of all, sine is positive, so it's going to be in the which two quadrants if we're between 0 and 2 pi? In 1 and 2, right? In the first quadrant, sine of what gives me 1/2? Sine of what? Sine of 30, yep. So that's pi over 6. All right, so pi over 6 is one of the possible solutions. The other one is, if I go ahead and draw my unit circle here. So the first one is pi over 6, right? And the other one has to be in the second quadrant and have a reference angle of pi over 6. So that angle is going to be what? How many pi over 6s should it be? Yeah, 5 pi over 6, one less than pi. So pi over 6 and 5 pi over 6 are the two solutions that 2 theta is equal to, because remember, we're taking sine of 2 theta, so when 2 theta is equal to pi over 6, or when 2 theta is equal to 5 pi over 6, that's when we're going to get 1/2 for sine of 2 theta. So that's the tricky part. So what we're going to do here is we're going to say, so 2 theta has to be equal to, and so I'm going to go back and just erase this, just so it all fits in here. So let's just rewrite this. So 2 theta has to be equal to pi over 6 plus 2 pi k, right? Or 2 theta has to be equal to 5 pi over 6 plus 2 pi k. Right? That's the general solution for both of those. Right? And what is this? Let's think about what this 2 theta is doing here, first of all. What is this? What type of transformation is this going to be on the function sine? It's going to be some type of transformation. What is this 2 theta going to do? Is it going to be some type of translation? Is it going to be a stretch or a shrink? What is that going to do to the graph of sine? It's going to be a horizontal shrink, right? Remember, horizontal stuff happens opposite of what you think it is. Which means if I shrink the whole thing, right, what's going to happen to sine? It's going to go through 2 full cycles between 0 and 2 theta, and 2, when theta here is between 0 and 2 pi, it's going to go through 2 full cycles, right, instead of only 1 full cycle, because when theta is equal to 2 pi, we're taking sine of 4 pi. And so it's already done 2 cycles by the time we get to 2 pi here. So that means we would expect to have double the number of solutions that we would normally have, because all of those zeros that were going to be out of the range before have been pushed back. And so what we're going to do here is we're going to say, well, then 2 theta has to equal pi over 6 plus 2 pi k, or 2 theta equals pi over 6 plus 2 pi k. So to solve for theta, we're just going to go ahead and divide the whole thing by 2. So pi over 12 plus pi k. Or theta is going to be equal to 5 pi over 12 plus pi k, right? And so pi over 12 and 5 pi over 12, those are 2 solutions. If we make k equals 0, then we get theta equals pi over 12 or 5 pi over 12, right? So those both work. Those are 2 solutions. But what if we make k 1? Then theta could equal pi over 12 plus pi, which is going to be 13 pi over 12, right? And then 5 pi over 12 plus pi is going to be 17 pi over 12. Do those both work? Are those both between 0 and 2 pi? Yep. What if we make k, and if we make k equal -1, we can see that these are both going to become negative, right? Because pi is bigger than pi over 12 and bigger than 5 pi over 12. So it makes sense to not make k negative. Make it 0, make it 1, and then make it 2, and see whenever you get out of the range. Let's make k equal to 2. Then we get theta equals what? What if we add another pi to this? We get 25 pi over 12, and we get another pi would give us 29 pi over 12. Are those inside the range? No. So we've gone too far at that point, and so we know that the only 4 solutions for theta that work that are in this domain are pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. So anytime we have a multiplier on the inside of our sign here, we have to remember we're going to go ahead and find the general solution, right? Regardless of forget about the domain for a second, find the general solution. That's whatever you have on the inside here, that's what that's equal to. And then go ahead and solve for theta, and then test all the values of k that are going to give you solutions that are within the domain you're looking for, and find all of the values of theta that fit in that domain by just going up or down with k, going up from 0, 1, 2 until you get outside of the domain, then go down until you get outside of the domain. And all the ones that are inside the domain are my solutions. All the ones that are outside, we can just toss away, and we'll end up with our solution here. So we got to be a little bit more careful when we start getting multipliers and anything going on inside of our sine or cosine function there. So I want you tangent of theta minus pi over 2 is equal to 1. I want you to solve this trigonometric equation, and by the way, we're going to restrict the domain from 0 to 2 pi. I want you to solve this trigonometric equation using that same strategy, where you figure out what theta minus pi over 2 has to be equal to, find a general solution for this, which is what theta minus pi over 2 is equal to, and then solve for theta, and then find all the values, and then test values of k to get all the possible solutions that are between 0 and 2 pi. Okay? Okay, so with this one right here, first thing we want to do is figure out where is tan equal to 1 between 0 and 2 pi, and then we'll go ahead and figure out the rest afterwards. So where is tan equal to 1? Tan is equal to 1 when what's true?
First and third quadrant.
Yep, first and third. Yeah, those are the quadrants it's 1 in, or where it's positive in. That's true. What are the angles going to be? Yep, pi over 4, because it's when sine and cosine are the same value, which is pi over 4, and in the third quadrant that would be 5 pi over 4. So that means theta minus pi over 2 is equal to pi over 4 plus, and what's the period of tangent? How often does it repeat itself? Pi, yeah, every pi. And then theta minus pi over 2 is equal to 5 pi over 4 plus pi k, right? And so we're just going to go ahead and try all the different values of tangent that'll get us there, right? And actually, one thing we actually don't need to, now that I'm thinking about it, we don't need to check 5 pi over 4 because once again, the period of tangent is 0 to pi. So if I add pi k to pi over 4, what am I going to get? I'm going to get 5 pi over 4. So instead of doing it that way, because we're going to get all sorts of repeats, when you're finding the general solution, just stick to the actual period of the function. So if it's sine or cosine, find the general solution, all the unique general solutions between 0 and 2 pi. But for tangent, just go between 0 and pi. So 5 pi over 4 is outside of that. So we're just going to go ahead and erase that because we're going to get it anyways. Right? So stay within the period of, for your first answer, stay within the period of the function that you're looking at. So we'll go ahead and we'll get theta is equal to, if we solve for theta, pi over 4 plus pi over 2 is going to be 3 pi over 4. Plus pi k, and so we want all the solutions that are going to give us be between 0 and 2 pi. So k can't be -1, right? Because if k is a -1, it's going to make it negative, and then it wouldn't be between there. So let's try. If k is equal to 0, then of course one of the solutions is theta equals 3 pi over 4. If k equals 1, the solution would be 3 pi over 4 plus pi, which would be 7 pi over 4. If k equals 2, theta would be 7 pi over 4 plus pi would be 11 pi over 4. And that is going to be bigger than 2 pi, so we can toss that one. Just like if we made k -1, right, we'd get theta is equal to negative pi over 4. And that would also be outside the range, so we toss that. And so the only two solutions that we get that are within the range of 0 to 2 pi are 3 pi over 4 and 7 pi over 4. Okay? So, once again, when we're initially finding our general solution, just find all the angles that are within the period of the function in question, and then use that to find your other answers by making k 0, 1, 2. Otherwise, if you were to have 5 pi over 4 in here, right, you're just going to get duplicates and repeats, which you don't want. So we'll forget about that one. Right. Let's go ahead and do that. All right. So there we go. Now lastly, calculator as well. All right, so all of the examples we've seen so far have involved special angles, and so we've been able to solve them without the use of a calculator. Unfortunately, in the real world, that doesn't always happen. So for instance, if you get a problem like the following, where I'm asking you to solve sine theta equals 0.3 on the interval 0 to 2 pi, right? You're not able to do that without a calculator because 0.3, 3/10, is not the value we get from sine for a special angle. So we have to use a calculator. So what we're going to do is we're actually going to use the inverse function. We're going to solve for theta by saying, well, if sine theta equals 0.3, then theta equals inverse sine of 0.3. Now, we have to remember, what is the range of inverse sine? Negative pi over 2 to, it's the range we had to restrict sine to make it 1 to 1, right, before we took the inverse. Sorry, it's the domain that we had to restrict sine to make it 1 to 1 and actually hit all the values, which is negative pi over 2 to pi over 2, right? Okay, so the range of that is going to be negative pi over 2 to pi over 2. So your calculator is only going to give you the angle that's between negative pi over 2 and pi over 2 that has that for a sine. And you have to figure out, okay, is that one of the solutions? Because that is that even between 0 and 2 pi? If it gives you a negative angle, if it gives you the angle in the fourth quadrant, you know that, well, that has the same reference angle, but you have to find the other angles in 0 to 2 pi that have that as a reference angle and that also have a positive value for sine. Right, so we're going to go ahead and our calculator will give us that theta in this case is equal to 0.304 or 305. So roughly, and I'm rounding here, of course, because it's an inexact answer. Right. So theta is about equal to 0.305. All right, so in radians, right, is that between 0 and 2 pi? That's in the first quadrant. It's between 0 and 2 pi. And so, and is it more than, what's pi over 2? Is it in the first quadrant? Pi over 2 is what? Nope, that would be 2 pi.
Oh, 2 pi.
Pi over 2 is 1.57. So 0.305 is less than pi over 2, so we know it's in the fourth quadrant. So if I were to go ahead and graph that theta, or draw that theta, right, it would be somewhere in here. All right, so the other quadrant where sine is positive, that's between 0 and 2 pi, is what? What's the other quadrant sine is positive?
Oh, wait, go.
Second quadrant. So we want an angle that has the same reference angle, which has a reference angle of 0.305 in the second quadrant here, right? So what angle would have how would I find that? We'd take theta, we would take 0.305 and do what with it to figure out what that angle would be? Yeah, pi minus 0.305 would be the other angle, and that's going to be, yeah, which is 2.837, let's say. So my two solutions would be theta equals 0.305 and 2.837, right? So you have to look at the angle that your calculator gives you. First of all, if it's not in the domain that you're asked for, then of course you're going to have to find another angle anyways. And even if it is, there's usually going to be another answer as well that's also going to be valid in the domain, unless it's a really restricted domain. And you want to find all the possible answers. And if I don't specify a domain, you still need you need all of the possible general solutions as well, in which case you'd still have to find this and then just add 2 pi k to both of these, right? So you have to remember that the calculator is only going to give you one possible answer. There's usually at least two answers. Sometimes there's only one, but usually there's at least two. Sometimes there's an infinite number, and so your calculator isn't the end of the game. That's going to give you one solution. You have to find the other ones. And sometimes the solution it gives you is not even the solution that you want. So you have to be very careful when using your calculator, knowing what the range of these inverse functions are. Okay? All right, so sometimes we have really weird trig equations that are what we call quadratic form trig equations. So for instance, if I had the equation 2 sine squared theta minus 3 sine theta plus 1 equals 0. This is a trigonometric equation in quadratic form because it has the same general form. We have a squared term, right? We have a linear term, and we have a constant term, just like we would have in a quadratic. So, and we saw examples like this with exponential equations as well, that were also exponential equations that were in quadratic form, and we factored those, and we're going to factor these as well. So how can I factor this out here? Right, I'm looking for, and I'm going to have to use fishbowl for this one, right? Because I'm looking for coefficients that are going to give me a quadratic term of 2, constant term of 1, and a middle term of -3. So I can fishbowl this, right? The coefficient on the first term is 2, so 1 and 2 are possible factors, as well as 2 and 1, and then 1 and 1. Which combination gives me a sum of 3? These guys, right? So I'm going to go ahead and factor this out as 2 sine, what? 2 sine theta, 2 sine theta, and sine theta. So 2 sine theta plus 1, or sorry, minus 1 and minus 3. They have to be this, or sorry, minus 1 and minus 1. They have to be the same sign, right? And so if I multiply these together, I'll get my quadratic here. So this will give me my sine 2 sine squared. These two will give me my plus 1, and then negative sine theta minus 2 sine theta gives me -3 sine theta. Okay. Now, after factoring, how do we finish solving quadratics? Yeah, set each of the terms equal to 0, so 2 sine theta minus 1, set that equal to 0, or sine theta minus 1 equals 0. Oh, and I should have also specified that there is a domain. Theta should be between 0 and 2 pi. All right, and so we'll go ahead and finish solving that. We'll end up getting sine theta is equal to 1/2, or sine theta equals 1. Okay. So between 0 and 2 pi, which values of theta give me a sine of 1/2? Sine of what equals 1/2? 30, yes. So which is pi over 6. And what's the other quadrant that it's positive in? So what's the reference angle of pi over 6 in the second quadrant? 5 pi over 6. And then over here, theta, where is sine equal to 1? Positive 1. Where is it equal to 1? That's an easy one. What? 90, pi over 2. So my solutions are pi over 6, 5 pi over 6, and pi over 2. All right, so if we see a trigonometric equation in quadratic form, we start off by factoring it. We set the two factors equal to 0, and then we solve the rest of those the same way that we have solved them in the past. So sometimes in more complex equations, it's helpful to use identities to help us solve the equations. So for instance, the following equation, if I have 3 cosine theta plus 3 is equal to 2 sine squared theta. So this is a trigonometric equation that it's not just a quadratic the way I'm looking at it right now. It's not a simple one that I can just set cosine or sine equal to 0 and then solve. So I have to be clever here. And what I'm going to do is I'm going to say, well, if I have 3 cosine theta plus 3 is equal to 2 sine squared theta, I want to try and use an identity to get this in terms of something that I can handle. And so the thing I'm thinking of right now is because I have a quadratic term right here for sine, and I have a linear term for cosine here, if I get this sine squared or this cosine in terms of the other one, so if I can get sine squared in terms of cosine or vice versa, then maybe I'll have a quadratic that I can factor and solve. So for sine squared, what's a trig identity that I could use for sine squared? What's the trig identity I could use for sine squared?
1 minus cosine.
Yep. 1 minus, no, just 1 minus cosine squared theta, right? Or there is the double angle, right? I could say, yeah, it could be cosine 2 theta. Sorry, it could be cosine squared theta minus cosine 2 theta, but 1 minus cosine squared theta from the Pythagorean identity is probably better because now I have it entirely in terms of cosine theta. And so what am I going to have here? I'm going to go ahead and just distribute. So I have 2 cosine theta plus 3 is equal to 2 minus 2 cosine squared theta. What type of trigonometric equation do I have now? That's a quadratic trig equation. So go ahead and finish solving that just like we did the last one. Okay, let's go ahead and finish this one up. So let's get it all on one side, just like we normally do with the quadratic. We get 2, put on the left side here, 2 cosine squared theta plus 3 cosine theta, and then we have plus 3, and we'll subtract 2 plus 1 equals 0, right? And then we'll go ahead and factor this out. Get 2 cosine theta and cosine theta, and then 1, and then 1, and they both have to be positive in this case. So we'll get 2 cosine theta plus 1 equals 0, or cosine theta plus 1 equals 0. So we'll end up getting cosine theta equals negative 1/2. Or cosine theta equals negative 1. So for the first one, right, cosine is equal to negative 1/2 if we're between, and we are restricting this from 0 to 2 pi. I should have mentioned that. Right, so theta is going to be equal to cosine's negative in the second and third quadrants. It's 1/2 when we have 60 degrees. So possible solutions would be 5 pi over 6 and 7 pi over 6. And then cosine theta equals negative 1 when we're at pi. So those are the 3 possible solutions to that equation right there. Okay, so using trigonometric identities is a powerful way of solving equations when they're not in the form that you want them to begin with. So I'm going to give you another one. I'm not going to give you any hints to use for this next one that's going to allow you to solve this trig equation. So if I have cosine 2 theta plus 3 is equal to 5 cosine theta, and I want to solve that for between 0 and 2 pi. Go ahead and give that a try. All right, so what trigonometric identity do you think we want to use here to get this into a form that we can solve?
2 cosine squared theta minus 1.
The double angle identity, yep. So yep, 2 cosine squared theta minus 1 plus 3 is equal to 5 cosine theta. Then we have a quadratic trig equation that we can solve. So we'll get 2 cosine squared theta minus 5 cosine theta plus 2 is equal to 0. And so we'll get 2 cosine theta. and cosine theta, and then we have to have 1 and 2, and they'll both be negative, so -2 and -1, so 2 times 2 is 4, and 1 times 1 is 1 for 5. So we'll get that cosine theta has to equal 1/2, or cosine theta has to equal 2. Now, can cosine theta ever equal 2? So there's no solution to that one, right? So the only solutions come from the cosine theta equaling 1/2 part. And so that would give us pi over 3, or the other one would be in the 4th quadrant, so 5 pi over 3, yeah. There we go. So sometimes we get parts of quadratics that are erroneous, right? That will give us no solution. That happens occasionally. And so there we go. We're all done. So the homework for tonight is the following. So the homework for tonight is from 2 different sections. On page 492 and page 500, I will copy and, will scan and email those out to everyone this afternoon, along with the solutions as usual. Have a great day.